Good morning, everyone. Thank you for coming. Today, I would be talking about Mad Max, which is a DSL that we have developed for explanatory decision making. Assume that you wanted to buy a car and the options in front of you were Honda and BMW. This looks like a deceptively simple problem, but in fact, it is hard because what attributes do you use to make this decision? Is it price? Is it safety? Is it efficiency? Or is it a combination of all of them? There may be various people influencing your decision, like your family, your friends, and even your car mechanic. And once you have the decision, you would also want an explanation for it so that you have trust in the decision making process. So let's try implementing this decision problem in Mad Max. So this is the table of numbers that we have for our problem, and this is the Mad Max encoding of our problem. And look at how straightforward it is to encode this problem in RDSL. So once we have encoded the problem, now we can try to find which is the better brand of car. So the first thing we could do is we can perform a component wise difference for Honda and BMW. So which gives us this set of numbers. But we are not able to interpret this value difference because we do not know how to compare a price advantage of $2,000 for Honda against a miles per gallon disadvantage of 2. And how do these attributes compare to safety? So in order to compare these numbers, we want to convert all these attribute values to common units. So this process of converting different attribute values in different units to a uniform range that can be compared is called normalization, and valuation is the function that implements normalization in Mad Max. So this is what my normalized attribute values for Honda and BMW look like. If we see here, all these values lie between 0 and 100. Not only that, corresponding to any given attribute, all the attribute values sum to 100. So this sums to 100, this sums to 100, and this sums to 100. Another interesting thing to note here is, look, Honda had an advantage in terms of price, and the normalized value reflects that. The normalized price value for Honda is 51.43, which is higher. Whereas if we look at MPG, BMW had an advantage because it has higher MPG and the normalized value reflects that as well. So we pass this information showing whether a low value is desirable or a high value of an attribute is desirable using using the valence class. And here we are saying that price has a negative valency, that is a lower value is desirable, and everything else has a positive valency, meaning the higher value is desirable. Alright, so once we have normalized values, now we can compare them. So the first thing that we want to do is compute a uh, attribute wise difference between Honda and BMW, giving us this set of numbers. And we can also compare the total score for Honda and BMW. So this tells us that Honda slightly edges BMW as the preferred car. So it is not uncommon to add an attribute value later in decision making. So let's assume we wanted to add Toyota to the mix. So this is our previous map, and we use the union function to add the various attribute values for Toyota, and this gives us the updated map called 3 cars. Alright, so far so good, but the real world decision making can be slightly more complex. For example, we could have family and friends having different preference for price, MPG and safety than experts. And finally, we could decide to give a different weightage to the opinion of family and friends than the experts. So this arrangement of various attributes in the form of a hierarchy is called analytic hierarchy process, or AHP for short, and this is one of the most important decision making tools, or theoretical decision making tools out there. And our aim with Mad Max is to implement the AHP model shown over here. Since in the first part of our talk, we already implemented the mapping corresponding to the bottom two levels, let's try implementing the other two mapping. The mapping between the feature and the opinion level, which is named feature opinions over here. So if we try reading one of the entries of this map, it tells me that personal preference for price is higher at 5 than the expert preference, which is 3. And finally, we have the map corresponding to the opinion level and the weight level over here. So here personal preference is assigned more importance by giving it a value, by giving it a weight of 0.6, whereas expert opinions are given a weight of 0.4. And finally, when we have all the maps, we can simply compose them together to get the final valuation, which we call car weights here. We can supply this final valuation to the total function, giving us the final scores for Honda and BMW. So here we see that Honda slightly edges past BMW. And we also have a very convenient function called winner in Mad Max that takes the final valuation and tells us the most preferred alternative, which is Honda here. So if we were only interested in decision making, we would be done now. But we have loftier goals in that we want to explain why Honda was preferred over BMW. And in order to do that, we use something called valuation traces. So valuation traces can be thought of as the log of the computation that resulted in these scores for Honda and BMW. And this is what valuation traces look like. So these valuation traces are obtained as a result of interaction of the various levels of our AHP. So if we look at one of the component of our valuation trace, this component takes into account the price for Honda, the personal preference for price, and how much was the personal preference weighted. So this component contributes 15.43 out of the total score of 50.36 of Honda. So if we add all these individual components, we get 50.36. Now, before we went ahead and used valuation traces for explanation, let's try cleaning them up a bit. So if we look at the weighted constructor, it appears in all the valuation components. And the reason it appears in all the valuation component is there is one, this is the component up at the top of our AHP model. So every component is going to share it. Since every component is going to share it, keeping it around does not make much sense, and removing it would not change our result. So if we got rid of our weighted constructor, this is what the cleaned up trace looks like. So every component that is present here would be present in the BMW as well. So price personal is present in both, price expert is present in both. So since we have the same component with different values present in both Honda and BMW, we can just go ahead and compute a element wise difference here. So this set of numbers tells us the element wise, give us the element wise difference between Honda and BMW. So the negative components are the components where BMW performs better, and these positive components are the components where Honda performs better. So in a way, these positive components explain why Honda was preferred over BMW. But if we look carefully here, we do not need all the positive components to explain why Honda was preferred, because the total value of the negative component is minus 1.23, and if we simply look at price personal and safety personal component, they themselves can overcome the total negative value. Now in this case, uh, we need only two components instead of four in order to explain the decision. And the minimal set of components needed to explain the decision are called minimal dominating sets. Look here the advantage of using minimal dominating sets is not very apparent, because all we are able to save is having to look at two components. But in a larger AHP where the number of components is high, the saving can be substantial. So the explanation that we saw on the last slide was unsatisfactory because it consisted of components from two different levels, feature level and the opinion level. And if we wanted, we could simply focus on the opinion level and aggregate over the feature level. So if we did that, we got a personal value of 0.72 and we got an expert component value of minus 0.01. So this tells me that although experts preferred BMW, personal preference was what led to the selection of Honda. So focus is a function that focuses on the dimension based on this type annotation, and we can also provide the focused value to the explanation to the explain function that can provide explanation in terms of the focused value. If we wanted, we could have focused over feature and aggregated over opinions. So if we did that, these are the set of numbers that we would end up with, and this tells me that price and safety are the feature or attributes where Honda has an advantage, and MPG is an attribute where BMW has an advantage. So price and safety is an explanation for why Honda was selected. So yet another form of explanation provided by our DSL is called sensitivity analysis. So it answers questions of the form, what is a change in the price of a car that can cause swap in rankings? So sensitivity is a function provided by our DSL that performs sensitivity analysis, and here we are trying to perform sensitivity analysis on the price attribute. So the output that we get is interesting, because this tells me that if the price of Honda was to if Honda were to increase its price by $1,085.34, BMW will become the preferred car. Or if BMW decided to slash its price by almost $1,125, it would become the preferred car. And this is perhaps the most interesting one. If Toyota decided to slash the price of its car by $20,500, even without a change in the price of Honda or BMW, their rankings would still be swapped. So in conclusion, our MadMax DSL allows for convenient encoding of AHP problems, which is also easy to maintain because this encoding is done in the source language itself. We are also able to provide explanations that could be tailored according to the requirement of the end users. Additionally, we have been able to extend our explanation technique called minimal dominating sets to work with hierarchical decomposition, which until now was able to work only with flat decompositions. That is all I have for you, and if you have any questions, I can try to answer it.